Chris Kurzik from AES. Welcome back. A little bit about our company, what we do. We provide equipment re-rating and fitness for service services, and reliability and safety studies, short-term staffing that we've been providing, and training and certification, materials and welding studies and investigations, and estimating and economic evaluations. And we've been getting into environmental studies like carbon footprint and emission studies. So let's dive into what we're going to work on today. Back, folks, we're going to continue with our study of the fatigue basics before we head out to ASME. And so this is part 3 of our series of 15-ish minute videos. So we looked at these topics earlier, and we're going to continue through our list. We are going to look at factors affecting weld fatigue and weld fatigue nucleation, weld fatigue performance testing in this series of 4 videos. So let's get at it. So we're going to look at the factors that affect the performance of weld joints. So this is the second part. So, we got the loading conditions, no surprise. We talked about that earlier. Talked about the material properties of, and remember with weld joints, we have 3 different material properties. We have the parent material, which is the joining materials, and then we've got the weld itself, and then we've got the heat affected zone, which is called the HAZ, which is the boundary between the weld and the parent metal. And so all those factors have to be considered when you look at the fatigue performance. So as a result, it's more complicated, right? And so that's why when the performance of a weld is also determined by its weld procedure, which we'll look at in more detail. So the factors that affect the performance of weld joints. So load conditions, material properties, the type of weld joints, okay? So, and the surface conditions of the weld, okay? Let's go back and look at this one again, some more detail here. So the nucleation stage in weld. So the surface nucleation stage in welded joints is influenced by surface irregularities. So we got weld ripples. We got weld discontinuities acting as stress riser. We've got residual stresses that enhance or reduce the surface nucleation stage depending upon external loading and orientation. And so, residual stresses, there's strategies to reduce those. And, stress risers is basically like looking at the shape of the welding surface and looking at that, and surface irregularities, so, taking precautions with that. So we're going to look some more into detail into this. So when we look at the parent material, and we have a part with no welds that's under fatigue, and then we have a part with fatigue, joints that have welds tend to fail sooner than parts that don't have welds, because even though the shape is identical and everything's the same, they should be the same but the problem with weld joints is they have many undesirable properties and they're hard to control. So sometimes designs are in high fatigue situations. They tend to remove the welds by using casting or forging or moving welds away from high fatigue areas. But it's not because the weld joint itself is weaker. It's because of the properties. Okay. So we continue to look at the factors that are affecting the performance of welds. So we have these undesirable properties. So what are these properties? I'll give you some examples here. So we've got the weld joint configuration. We've got the joint load is carrying or non-load carrying type loads. And so, we can have different loads and different weld configurations. We have stress raisers. We've got residual stresses. We've got, hard and softening of the HAZ zone. There's irregular or rough surfaces of the weld mount. And we have inhomogeneity with respect to the composition, the metallurgy, and the corrosion and mechanical properties. So because the joint, you look at the weld joint, I mean, you've got this Whitman-Staton type structure in the middle with, very soft elongated grains inside the weld, and then towards the edge you got this heat affected zone, and then you have the weld. So there's different weld structures. So that's reason why we have issues with welds and fatigue. So factors that affect the performance of welds. So we have weld joint fatigue is determined by the severity of properties. And they say that a weld joint life can be up to 0.15 times the fatigue life of a corresponding base component, which is the parent material. So if you had, they're saying that if you had a part that was not was just cast or forged and there was no welds, it could have a considerably longer part. But if you introduced a weld, then you could drop the lifespan of that part considerably if you don't have the controls. So this is something we found in literature. I'd love to hear what your thoughts are on that, and that would be great. Welding fatigue performance improvement strategies. Methods to improve the weld joints include increasing the load carrying capacity. So that means increasing the size of the weld and maybe the thickness of the parent material, as a way of doing it. Sometimes we've seen in the past where the welds were too small and the load capacity was too high, and then we saw cracking. We see that sometimes on shaking structures, like material handling structures. We just end up putting more weld. And also another way is to reduce the stress risers. So it's very common in a lot of specifications in industry specifications where there's fatigue. They're fatigue type vessels or equipment, and they ask for removal by grinding. In Section 8, Division 2, it's a requirement to reduce stress risers. Now, fatigue factors, we're going to look at some more here. So, we look at the type of stress. So, elongation bending stress is the worst type of stress because you're elongating the part. Now, if you have, compression stress, then it's not as bad, right? But the elongation is, and we'll talk more about that in a little bit. So we've got, what is our maximum and minimum stresses? So these affect the performance of the joint. We've got this, the mean stress, which we will talk about, and I've given them this symbol. There's a lot of symbols out in literature. There's a lot of different reference points. I'm going to use this one because this one sort of matches closer to ASME. So the mean stress is defined as half of the maximum and the minimum stresses. Then we've got the stress range, which is the change in stress. So it's the maximum stress minus the minimum stress. Okay, so it should be twice the mean stress. And then we got the stress ratio, which is really important because it helps us to understand the design, and it's called it's the minimum to maximum stress ratio. And we've got the stress amplitude and the frequency. I think that covers it. And one more thing here. So this is the terminology that is used to describe, the fatigue characteristics and the, in fracture mechanics, is the mean stress ratio and the stress range and mean stress range and stress ratio. Okay, and they're important because there are the issues when we do like weld testing, because ASME has an option. If you can't use B31J or B31.3 or the stress, the canned stuff, because the shape is too complicated, you can use weld testing, but then they need to be tested with these three factors taken into account. Take a look at the types of stress with little charts so that we can sort of organize this. So the first type of stress that is called the zero to tension pulsating stress. This is where the mean stress and the amplitude stress, are equal. And this is because SR is 0, it's at the top, it's a positive, basically a positive number, but it's the ratio is 0. So that means it's never in compression. It's called a pulsating load. The second type of stress is called a fully reversed. Okay, that's when it goes in the fully tension and fully compressed. So the negative is the compression and the positive is the tension, and they basically cancel each other out. So when you see an SR ratio of -1, that means it's a fully reversed type of stress, and then the mean stress is 0. So the third type is called the compression tension cyclic stress. And this is the one that one should be more worried about, that because it's always in constant, like the overall stress is in constant tension, and so in this case, this mean stress is greater than 0. And SR is greater than 1. And the final one is the one that we get in the field data, and it's a complex one. It's called irregular random. Other authors call it the complex stress cycle. And there's some help in ASTM E1049 that you should be aware of how to organize and analyze these cycles so that you can get useful information. There's also guidance in Section 8, Division 2, and if there's a request, we can do some more videos talking about fatigue cycling, which is looked at quite heavily in Division 2. Maximum stress. So if I increase the maximum tensile stress or the shear stress, then I will reduce the fatigue life. Okay, so when I put parts under tension, then the rate of crack growth will increase. Now, if I have the mean stress, which is defined as the stress amplitude, which is half the maximum minus the minimum, if the mean tensile stress results in lower fatigue life more than the compressive and the 0 mean stress. Okay, those are some of the fundamental rules. And if you increase the tensile mean stress, and you'll decrease the number of cycles required for fatigue nucleation and propagation of the cracks. Now, this is an interesting curve because this shows us, our 0 mean stress there, and then we look at our compression, which is higher, and then our tension, which is lower. And then we go on to the maximum one, which is we look at the max minus the minimum. We'll go into that one. So we have as the we increase the stress range, we reduce the fatigue. And so a stress in the zero range means there's no fluctuation in the magnitude of the load, something to remember. And so so this load is static in nature. Therefore, you don't need to, material's not experiencing any fatigue if it's fully reversible. So that's considered to be, zero stress range. And that's important, right? So the stress ratio is the minimum minus the maximum ratio. And as the stress ratio is reduced, then you get a greater fluctuation in the fatigue. And a stress ratio of 0.1 means that the maximum stress is 10 times the minimum stress. So it's important to sort of read what those values are in fracture mechanics. So SR, if SR is -1, then the load fluctuates equally on tension and in compression, which is a good thing, right? And then typically when they do fatigue testing in welding, they look at stress ratios of 0.1, 0.2, and 0.5. So we're going to look at frequency of fatigue loading, dispel some myths. So the frequency of fatigue loading has little influence on fatigue performance. It really has to do with the amplitude. But the increase in frequency in loading generally increases the fatigue life of the part. So this is what we found out when we were doing or looking at that. So it's something to consider. So I hope that you found this presentation useful and valuable to you. This was provided by Athabasca Engineering Solutions. We'd love to hear your feedback and your thoughts on further videos. And we'd love to hear from you. Maybe we can do some business. Please subscribe to our channel so you don't miss a thing. Take care for now.